So, Amol, why don't you take it away? And we'll be speaking about limit shapes and local statistics for the stochastic six-vertex model.
Okay, thanks a lot, Ivan, for the introduction. So is my screen shared? It says that sharing is pause and bring your shared window to the front. Do you see the?
I see a screen. I'm not.
Is it
Yeah,
big? Like,
it's not totally big. It has like some junk on the side and on the top, so it's not like the full
oh,
screen mode yet.
interesting. Okay, okay.
Now it's like super zoomed in. Now it's back to what it was.
Okay, okay, whatever. Okay,
But this is fine, I think.
yeah, we can just do this. Okay, so okay, so let me just start by describing the model. So I think we've seen it before in several other talks in this summer school, but I'll just redefine it. So we'll fix some domain of Z2. Let's call it lambda. In each vertex of lambda, we'll assign one of 6 possible arrow configurations. So at each vertex, there are going to be some number of incoming arrows and some number of outgoing arrows that satisfy the property that the number of incoming arrows is equal to the number of outgoing arrows. And this is called spin conservation. So there are, as a consequence of the spin conservation, which you can quickly see, is that there are 6 possible local configurations at each site of arrows. So here is the one, the empty one, where no arrows come in and none come out. Here is the full one where 2 arrows come in and 2 come out. And there are going to be 4 more where 1 arrow comes in and 1 arrow comes out at the various possible edges. So these are going to be local configurations for our model, and the model is called the 6-vertex model because there are 6 possible choices of the vertices. So 6-vertex ensemble is simply an assignment of one of these 6 possibilities to each vertex in a consistent way. And what I mean when I say consistent is sort of the natural thing. Namely, if this arrow here where my cursor is has a horizontal arrow exiting from it, then the adjacent vertex has to have a horizontal arrow entering it. Okay. So now the spin conservation tells you that the number of incoming arrows is equal to the number of outgoing arrows. What that quickly implies is that you can view this model as a series of upright directed paths where paths can touch but they can't cross. So for instance here, you see a path going left, coming in horizontally and then exiting vertically, and likewise here you see this path sort of zigzagging, etc. So boundary conditions of this model then prescribe where the paths enter and exit the domain. Okay, so in spirit of classical statistical mechanics, if we have some 6-vertex ensemble E, let's fix some weights, A1, A2, B1, B2, and C1 and C2, and we'll assign to each of the 6 vertices a vertex weight. So as follows, so just as depicted here, you have these 2, the empty is given weight A1, the full is given weight A2, the vertical is given weight B1, the horizontal is given weight B2, and the corners are given weight C1 and C2. And the weight of the full ensemble is A1 to the number of A1 vertices, A2 to the number of A2 vertices, etc. For example, I've drawn an example here. So you have the 6-vertex ensemble here. You can quickly see that there are 8 A1 vertices. So they're here, here, and these 6. So you have A1 to the 8, etc. So a probability measure, you can then define a probability measure on the set of all possible ensembles. And that's simply given by it's proportional to the weight of the ensemble, but then of course to make it a probability measure, you have to divide out by the sum of all possible weights, which is the partition function. So this is the 6-vertex model, and what we're interested in is understanding large-scale behaviors of it. How does it behave as the domain size gets very, very large? So in this talk, I'll be interested in a special case of the 6-vertex corresponding to where these weights are stochastic. So this model was introduced, the specialization of the model was studied first by Guo and Spohn in 1992. And the specialization is as follows. The first A1 and A2 weights, these 2 weights in the beginning, are given weight 1. Then the horizontal and vertical weights are given weights B2 and B1, and the corner weights are given weights 1 minus B1 and 1 minus B2. So the stochasticity property is the following. It's that if you fix the incoming configuration, then the sum of the weights over all outgoing configurations is equal to 1. So for example, if there are no arrows incoming, then the arrow conservation implies that you can't have any arrows outgoing. There's only one possibility, which is this one, and its weight is 1. Likewise, if you have 2 arrows incoming, then of course there's again only one possibility, and that has weight 1. Now, if there's one vertical arrow incoming, then that arrow can do one of two things. It can go out vertically or it can go out horizontally. But then you see the weight of these, the sum of the weights is equal to B1 plus 1 minus B1, which is 1. And likewise horizontal for the horizontal situation. Okay, so if I, under free exit data, so if I say run this model on the upper half plane, so on the discrete upper half plane, and I fix some incoming configuration of arrows like I've done so here, and I sum over all possible outgoing configurations, so I don't put any sort of upper boundary restriction on that, then this model enables a row-to-row Markovian sampling procedure, which I'll describe. So I start with the leftmost. So imagine for the moment, for simplicity, that there are only finitely many arrows entering the model. So I start with the leftmost arrow. I see that it comes up. I look at this sort of cheat sheet, and I look at all possible ways an arrow can enter vertically at the vertex. And there's this one, and there's this one. I flip a coin with probability B1, the arrow goes up, and with probability 1 minus B1, the arrow goes to the right. So let's say flip tails, so the arrow goes right, and I have 1 minus B1 here. And then I iterate. So now I see at this vertex, there are 2 arrows incoming. So I look at this chart again, and I see that there's only one possibility. And so the situation is forced, both arrows have to exit. And I multiply that by 1, and then I iterate. Okay, I look here, I see the arrow is incoming horizontally. There are 2 possibilities. So let's say it goes vertically again. So I gather our weight 1 minus B2, and then I keep going. Okay, and then so this is the evolution. This is one time step you might imagine of evolution, where this row is filled in at the next. So vertical arrows are now placed on the next row, and then I can iterate this sort of row by row, and I will get something that looks like this. Okay, so in that way there is this sort of Markovian sampling procedure of the model. Okay. So again, I'm going to be interested in large-scale behaviors, and to make that precise, it will be convenient to introduce what's known as a height function. So we'll assign to each face an integer, and it'll satisfy the following local constraints. So I've just drawn all 6 possible vertices. I've fixed, at each vertex, there are 4 faces adjacent to it. And I've fixed the bottom left face at each vertex to be some integer h, and I've told you, based on the arrow configuration of that vertex, how to fill in the face, the other 3 faces around it. Okay, so these rules might seem somewhat arbitrary at the moment, but you should really look here for the real rules. And so what this is saying is that every time you cross an arrow from the left, every time you sort of traverse an arrow from the left, the height function drops by 1. Every time you don't cross an arrow, the height function stays the same here and here. And every time you cross an arrow, a horizontal arrow from the bottom, the height function increases by 1. So I mean, this is just the rules that are being applied to form this chart. Okay, so I fix the height function at some favorite vertex of the model. I'll typically normalize the height function to be 0 at the origin, and then I use these rules to propagate the height function to everywhere else in the lattice. So what you can say is you can sort of view h of u as counting how many paths exist to the right of u. Although this is up to a global shift. So for example, here, if there are h paths to the right of this face here, then after I cross one of these paths, they're going to be h minus 1. And likewise, there's a similar thing going on here. So now there's a bijection. If I have a 6-vertex ensemble, this provides me a way of producing the height function up to a global shift. And likewise, if I have a height function, then I can recover the 6-vertex ensemble from it. So this is a bijection, again, up to global shift. So I've just given you an example. Here is the origin, say, and you know, let's say I cross this arrow from the left, the height function drops by 1. I don't cross it, the height function stays the same, and then etc. So you can sort of generate the height function in this way. And once again, my basic question is, what is the asymptotic behavior of the stochastic 6-vertex model? So I'll state 2 results here. One is a limit shape theorem, which addresses the global behavior of the model. And the next is a local statistics theorem, which addresses the local behavior of the model. So let me start with the former. okay, so it's the limit shape. So again, the question in this case that I'm trying to address is, what is the global large-scale behavior of this stochastic six-vertex model? So, so what we're going to do is we're going to consider the stochastic six-vertex model again on this discrete upper half plane. So Z cross the non-negative integers, and we'll introduce some. So the boundary conditions for this model are dictated by the locations of these guys, the incoming arrows on the bottommost row. And that isn't bijection more, so less with the height function when I specify the second the y coordinate to 0. Okay, so if I have that height function, then I can recover the locations of the incoming arrows. So I'm gonna say that this initial data sort of scales to some profile, which I'll call psi. So I'll fix some 1 Lipschitz function psi. The function had better be 1 Lipschitz because the height function is 1 Lipschitz. And I'll assume that H, this initial profile converges to psi. So so like n inverse times Hn of n of x converges to psi. So this is the typical scaling for limit shapes. And I'll just make a choice. I mean, I don't want to set B1 equal to B2 because then the behavior will be different. I want the model to be genuinely asymmetric. So I'll set B1 to be less than B2. And I'll define these functions phi and kappa. So kappa is 1 minus B1 over 1 minus B2, and that's at least 1. And then this phi is defined in this way. I'll give a meaning to phi later, but at the moment it's just a formula. Okay, so here's the theorem. So it's a limit shape theorem. So I have the height function at the on the bottommost row. I have the height function on the y equals 0 line. And what this limit shape theorem tells me is that it tells me how to get the height function everywhere else with high probability. So with high probability, sorry, this t should be an n. Sorry about that. So if I look at this height function at some coordinate xy, I scale xy by n. I run this thing so you can imagine me running the stochastic six-vertex model for time yn. Then if I normalize by n, this height function will converge to a deterministic profile, which I've called this fancy, this math fract h of xy. And this deterministic profile solves a specific PDE. So it's initial data. Okay, so right. So the initial data for this PDE is given by h of x0 is equal to psi of x, as it had better be because of this profile, the scaling for the profile. And then it satisfies this PD here. So partial of y of h is equal to phi of minus partial of x of h. So now you have to be a little bit careful when you talk about this. Oh my gosh. Okay, so there's a typo here. There should not be an equal 0. Ignore the equal 0. So just, okay, never mind. Yeah, okay, so ignore the equal 0. So this, partial y of x is equal to phi of minus partial of x of h. So now, again, you have to be a little bit careful about what you mean by the solution to this PDE. You might hope that this PDE has strong solutions, but it doesn't. There exists, so this PDE does not have strong solutions. And the weak solutions to this PDE are not unique. So there are multiple different h's that satisfy this PDE uniquely. So what you have to do is you have to pick the physically relevant solution, which is sometimes known as the entropy solution. So I won't go into depth with that at the moment. I will later sort of describe a family of properties that uniquely characterize this entropy solution, so that you can view that as almost the definition. But I won't do that for another half hour about. Okay, so I mentioned this theorem. The domain is this discrete upper half plane. It also applies in other domains such as the cylinder or quadrant. I just decided to state it on this domain for convenience. Okay, so are there any questions about this limit shape theorem? Okay, so no. Okay. Okay. So again, I've just rewritten the limit shape theorem up here. And I'll just give you a little bit of background about it. So first, it was predicted in 1992 when the model was originally introduced by Guo and Spohn. And their prediction for it was based on a hydrodynamic limit for an underlying particle system. So I'll get to that later. But it was basically based on the theory of interacting particle systems. And such a theory, the theory of interacting particle systems, such hydrodynamical limit theory, is well developed in the case of continuous time exclusion process, such as the ASEP. But something to keep in mind for the stochastic six-vertex model is that it's discrete time and it's sequential. So the discrete time is maybe not so bad, but what's really annoying about it is that it's sequential in the sense that I actually have to, start the model. If I run this thing, I have to actually start from the leftmost guy, and that affects what the later particles do. What the particles to the right of it do. So it actually, the ordering of how I evolve these, how these arrows evolve is actually important. So what that, in practice, what that renders the Markov generator of this model a huge pain to deal with, which is why at least I did not see a quick way of directly adapting a lot of the well-known continuous time theory to this discrete time model. So another derivation, heuristic derivation of this result was due to Reshetnikov and Sridhar in 2016. And it was based on a heuristic variational principle. So again, this is just an aside. So I won't go into too much detail with it, but if you were here for Rick's classes, then you might have seen the variational principle for certain types of statistical mechanical models. And there's just a note of caution I want to say here, is that when you prove a limit shape result for a statistical mechanical model through a variational principle, you actually oftentimes get more than just the limit shape result. You get a large deviations principle for it. And this large deviations principle approximately states the following. If you differ from the limit shape by a macroscopic amount, the probability of that happening scales like e to the minus n squared, where n is the size of your lattice. So there's a large deviations of order e to the minus n squared. Okay, now for the stochastic six-vertex model, the situation is actually quite different from that. Actually, this is somewhat similar to what Li Chen was describing in his previous talk. If the probability of your height function being much larger than the limit shape is like e to the minus n squared, but the probability of being much smaller than the limit shape is e to the minus n. So this is a sort of an asymmetric large deviations phenomenon that occurs for the stochastic six-vertex model. So what that means, at least what the point I'm trying to get across here is that I'm not trying to say that this variational principle cannot be made rigorous, although I don't know how to make it rigorous. But if it does, then it would be somewhat unusual because you would sort of be getting the result, but not getting the things that always come along with it. Namely, you would not be getting the standard large deviations principle that you would get. So something has to be different for this model. Okay, and the last sort of historical remark I want to make about it is that it was proven for special cases of so-called Riemann profiles. The Riemann profile, so I'm taking the derivative of psi, which is more or less giving you the density of incoming arrows. So that's like that's like a step function. So to the right of 0, it's some rho, and to the left of 0, it's some lambda. And for rho bigger than lambda, this theorem was more or less proven by results of Borden, Corwin, and Garland, and also myself and Borden. Okay. So now, okay, so those are the limit shape results. Let me talk about the local statistics now. So I'll try to talk a little bit about the, yeah, right. So, okay, so the basic question here is, let's suppose I take the stochastic six-vertex model on some large domain. And let's suppose I take some vertex in this domain. So it's this tiny green spot, which you might not even be able to see. And I zoom in around it. So I take a say a 10 by 10 neighborhood of that vertex. So I've sort of zoomed that out here. Zoom that in here. So this yields a random six vertex ensemble in that neighborhood, and it's going to be random because the six vertex ensemble was random in the first place. And the local statistics question is, what is the law of this random ensemble? Okay, so in principle, I can get a huge number of, I can get a huge number of possible six vertex ensembles, and I want to know what is the law of this ensemble. And that tells me various things. For example, that would tell me what the probability of say the joint law of this vertex being a corner and say this vertex being a straight line. So it would give me all sorts of local correlation functions for this model if I had access to the law of that ensemble. Okay, so I'll give you a feeling of candidate. So okay, so I want to, just in case you've maybe not seen this before, I just want to describe the standard statistical mechanical, I guess, or the physics mantra that, or philosophy that people, that give you sort of a candidate of possible descriptions for how these local statistics should look. So one thing to keep in mind is as the size of this neighborhood tends to infinity, but make it tend to infinity super slowly with n, so log n or something like that. This neighborhood will exhaust all of the full lattice. So what you're actually getting is a random six vertex ensemble on the full plane. Okay. So a priori, what you want to say is something like the law of this full plane six vertex ensemble had better be given by a six vertex model on the full plane. But the problem is that the six vertex model was defined by these weights, these W weights, and these weights are defined by products of vertices, products of vertex weights. And these vertex weights, I mean, this product is not convergent, or it's zero if I look at the model on the infinite plane. So what you do is you consider Gibbs measures instead, which are the following. So a measure mu is if I take a measure mu on the family of all possible six vertex ensembles on some infinite domain lambda, let's suppose I restrict to some finite domain lambda prime. So I've drawn that, I've depicted that by this sort of dash square here. I sample a big six vertex ensemble on all of lambda, and then I condition on everything outside of the subdomain lambda prime. Then I'll say that mu satisfies the Gibbs property if conditional on everything outside of lambda prime. On the inside of lambda prime, it is a six vertex model. So it is a six vertex model, which makes sense because now lambda prime is finite. So so more precisely what I mean is the probability that the ensemble, the restriction to the ensemble is some f, conditional on everything outside, is proportional to the weight of f. Okay, so now what should be hopefully quickly, so what can be quickly shown is that if I take the six vertex model in any finite domain, it certainly satisfies the Gibbs property. So what you can certainly believe is that as I let the domain size tend to infinity, this Gibbs property is retained. That is, any local statistics, the limiting local statistics have better satisfied the Gibbs property as well. So this is what I've tried to describe here, that Gibbs measures are candidates for local statistics. But the problem is that there are too many Gibbs measures for the six vertex model. So what we do is often we restrict to pure states, which are translation invariant extremal Gibbs measures. So a measure is a translation invariant if it's invariant under translation, so under shifts of Z2. And it's natural to expect the local statistics to be translation invariant because, if I look here, if I just move everything to the right by one, globally it shouldn't have any impact. So it's natural to expect that sort of the law shouldn't be so sensitive to where exactly it shouldn't be so sensitive to microscopic changes in where I look. Now the extremality is less obvious why it should be true, but okay, but here's the definition. So a measure is extremal if whenever I can decompose mu into a non-trivial linear combination of two other translation invariant measures, then we have to have that this linear combination was in fact trivial. So if mu is equal to p mu1 plus 1 minus p mu2, then you have to have that mu is equal to mu1 is equal to mu2. So they're all the same. So as I said, it's a lot less obvious why this measure had better be, even heuristically, why this measure had better be extremal. But anyway, this is just the definition of a pure state, that it's translation invariant and it's extremal. So associated with any pure state is a slope, ST. So S you should view as the, in this context, it's the probability of any vertical arrow being occupied. And again, this is not dependent on which edge I pick. So I'm looking at an edge and I ask what the probability that it's occupied by a vertical arrow. By the translation invariance, it doesn't depend on which edge I pick. And likewise, the T is the probability that a horizontal arrow is occupied. So in terms of the height function, S is h of 0, say 0, 0 minus h of 1, 1, which you can kind of view as the negative of the x derivative of the limit shape. And T is h of 0, 1 minus h of 0, 0, which is kind of the y derivative of the limit shape. So the general prediction in this context for statistical mechanical models is that the local statistics, and any point are governed by a pure state whose slope is determined by the limit shape. So, so more precisely, if I pick some vertex v, which is like nx and y in the domain, then the pure state, then the local statistics, if I zoom in, if I take that sort of O1 by O1 neighborhood around that point, then the local statistics should be given by a pure state of slope this. So actually this. So minus partial x of x minus, and then partial y of y. Okay, so we can actually, if we recall the limit shape result that I had from the previous slide, we can actually derive sort of, if we believe this prediction, we can derive a consequence of it, which is that, recall that the limit shape said that the partial y of h was equal to phi of minus partial x of h of xy. So what that's telling you is that these two components of the slope should actually be related, namely t should be phi of s. So these if you believe this prediction, then what it's telling you is that the local statistics on any point should be given by some slope st where t is phi of s. Okay, now implicit in this prediction is the fact that this pure state, I've just defined this pure state. I haven't told you whether it is unique or whether or not it even exists. So this is actually a highly non-trivial question. And for models which are known as simply attractive gradient models, it's known that any slope admits a unique pure state of that slope. However, this six-vertex model, ferroelectric or the stochastic six-vertex model, is not simply attractive. So it does not fall into this class of models where you have this uniqueness and existence result. Okay, so let me start stating some more theorems then. Okay, so the first theorem is that if I fix some st in 0, 1, such that t is phi of s or s is phi of t, then there is a unique pure state for this model. So at least we can now, then there is a unique pure state of this model. So at least we can start talking about what this prediction, we can at least make sense of this prediction now. So now the second theorem is more or less going to prove this prediction. So we're again going to consider the stochastic six-vertex model with free exit data. So I pick some initial data, which is given by, again, normalized to be psi, and then I let this thing go without restricting on the exit data. And then I again take this entropy solution to this PDE I described before with the correct initial data. I pick some vertex, so I pick some sort of, you should view xy sort of the macroscopic point in the domain. And I'll pick it so that it's a continuity point of the gradient of, so this should be the gradient of h, not just h itself. So x of y is a continuity point of the gradient of h. And the theorem is that as n to infinity, the local statistics of this vertex ensemble around this rescaled vertex n of x, n of y converges to this mu of s of t. Okay, so the local statistics are indeed given by this pure state of the correct slope. Okay, so from the perspective of interacting particle systems, this can be viewed as a convergence to local equilibrium result. And again, for continuous time models, this is reasonably well developed. I've cited one work, although there are various, by Bahaduran and Mountford in 2006, who showed that the sort of convergence to local equilibrium holds oh, sorry. So I guess Li Chang asked the question: does s equal to 5t just means swapping the meaning of the two variables? Yeah, more or less. In response to Li Chang's question, yeah, you can get it from a symmetry, so which amounts to swapping the two variables. Okay, so these sorts of conversions to local equilibrium results are known for continuous time processes such as the ASAP, but oh, so there's another question. Okay, thanks. No problem. So, but again, this model is discrete time, so and sequential, so it's somewhat different. Okay. So, any questions about these local statistics results? No. Okay. Okay. So I'll give you one more theorem here, which is so what I've drawn here is sort of the space of all possible slopes. So all the slopes are on the square 0, 1 cross 0, 1. And what I've drawn in blue here are these curves t is equal to 5s or s is equal to 5t. Now, remember that in the simply attractive models, whatever those mean, I mean, I'm not going to define them. The prediction is, I mean, the theorem there is that every possible slope, so if I pick any point in the square, then you have a unique pure state. Okay, so the theorem, so our recent theorem is that if I pick a point between these two curves, so if s is less than t is less than 5s, there is no pure state for the stochastic six-vertex model of that slope. So again, this phenomenon does not occur for simply attractive gradient models. So I mean, this is not this notion that the model is just simply attractive is not just a technical. The fact that the stochastic six-vertex model is not simply attractive is not just a technicality condition. I mean, it actually changes the behavior of the pure states of this model. So Bookschmidt, this was actually predicted. I don't want to, I mean, claim credit for the phenomenon at least. It was predicted by Bookman and Shor, physicists in 1995. Okay. So I've described okay, so by the way, one thing I should say is that, so we have pure states on the green curves. We have no pure state, sorry, on the blue curves. We have no pure states in this red region, and pure states on the boundary of this box are sort of trivial. I won't go into them. In the white region, it's still an open question. So we don't know. I mean, presumably the prediction is that there should be a unique pure state in this white region outside of this sort of lens, but it's not known how to prove it. Okay. So the next thing I want to do is describe to you, I've just told you this abstract notion of a pure state. But in the case of this stochastic six-vertex model on these blue curves, on this line t is equal to 5s, these pure states are actually very explicit and very friendly. So I want to take a few moments to describe to you how to get them and how they look. So the way in which you get them is the following. So you consider the stochastic six-vertex model on the quadrant. So again, these pure states are defined on the full plane, but I'll start out by defining them on the quadrant and then taking a limit. So we define, we consider the stochastic six-vertex model on the quadrant with what we call double-sided Bernoulli initial data. So what that means is that sites on the y-axis are independently entry sites for paths with probability t. So, you know, at each possible place where a horizontal arrow can be, I flip a coin with probability t. I let a path enter through there, and with probability 1 minus t, I don't. And likewise on the x-axis, we allow paths to enter with probability s. Okay. So if t is equal to at the special point where t is equal to 5s, then this double-sided TS Bernoullian right, so it should be ST, but double-sided Bernoulli initial data is stationary. And what I mean by that is that I take a model looking like this and I cut out a subquadrant of it, okay? And then I ask myself, okay, how are the paths entering through the subquadrant? And the answer is that they're going to be entering exactly as they did on the big quadrant. Namely, on this vertical line, they're going to be entering independently with probability t, or 5s, and on the horizontal line, they're going to be entering independently with probability s. So again, this sort of double-sided Bernoulli initial profile is translation invariant in the sense that if I cut out a small subquadrant of it, then I retain this double-sided Bernoulli property. So you can view this, for those people who have studied the ASEP in more detail, you can view this as sort of an analog of the fact that the Bernoulli profile is stationary for the ASEP. And I should say that this phenomenon is false if t is not equal to 5s. So this translation invariance of the stationarity is sensitive to the fact that t equals s. It's exact there and it's false everywhere else. Okay, so this defines how these things look on the quadrant. Now I have to define them on the plane, which is done by a limiting procedure. So I take this quadrant and let's say I shift it back down into the left by minus nn. Okay, so I get a new quadrant, and I run I take, you know, this 5ss double-sided Bernoulli initial profile on this bigger quadrant, and then I run it. Okay, so I'll call that measure. So now this is a measure on so it's still a quadrant, but now it's the quadrant whose corner is minus n comma minus n. So this defines a measure on all path ensembles, 6 vertex ensembles on that quadrant. Let's call it mu n of s. So now that stationarity property I was describing before basically told you that if I restrict to a subquadrant of this bigger quadrant, then this double-sided Bernoulli property is preserved. So in practice, what that means is that mu m of s is the restriction of mu n of s for any n m greater than m less than n. So what that allows me to do is now I can just shift this thing back all the way to negative infinity, and these measures are coherent with one another. So I can define a limit in that way. So now if I shift this thing all the way back, then I get a measure on the full plane, and that is well defined, and that is my pure state mu of st. So this actually proves the translation invariance. The proof of the translation invariance is more or less in what I said. The proof of the extremality is not hard, but it takes a little bit. It's like a page. So anyway, this gives you a pure state of which I'll call mu of s or mu of st of slope st for this model. And this is actually useful. I mean, you can actually compute things with it. So if you want to determine local probabilities, you can do that, for example. So if I let chi of v denote the indicator that that a vertical arrow is exiting from a vertex v. So like chi of v is 1 here and say 0 here. Then the probability that say 2 consecutive chi's are equal. So chi of 0, 0 times chi of, I can compute this correlation function, for example, that 2 consecutive horizontally consecutive sites are occupied by, have a vertical arrow exiting from them. That's just s squared. And that's sort of transparent from everything I talked about here. I can just pick a quadrant that cuts along this line, and because this is independent, because the profile is double-sided Bernoulli, I know that the probabilities of these 2 sites being occupied are independent with probability s. So that gives me that s squared. Okay. Now if I take, so this is what happens if I take 2 sites which are horizontally adjacent. Now let's suppose I take 2 sites which are diagonally adjacent. So here, it's a computation. You can sort of compute it using this sampling procedure. It's s squared plus a correction term. That correction term is given by s times 1 minus s times 1 minus b1 times 1 minus b2. So it's a little bit bigger than s squared. So it's a little bit bigger than if they were just independent. So so you actually have positive correlations for this model, for example. Okay. So one useful property of this construction is in computing local probabilities, local correlation functions. Another useful feature of it is that you can actually use it to prove height fluctuation results. So how the height fluctuates under this measure mu of st. But I won't get there. I don't want to go there for now. And instead, what I'll try to do in the last, sorry, Evan, what is my time? Is it 50 minutes or an hour?
You can take up to an hour. It's fine.
Okay.
So you have 19 minutes.
Okay. So for the remaining part of the talk, I want to try outlining the proof of this limit shape result. The local statistics result is actually a bit harder to prove, so I won't try to get there in this talk, but I will try to give you some of the main features of how the proof works for the limit shape result. And the advantage, I think, since this is a summer school in integral probability, I think that a lot of these, so the proof basically proceeds by showing that double-sided Bernoulli profiles are sufficient to characterize the full limit shape for arbitrary profiles. So the limit shape result was proven, I mean, the theorem was stated for all initial data, but the way in which this proof proceeds is by proving it for double-sided initial profiles, and then sort of bootstrapping from those to all initial profiles. And the advantage of these double-sided initial profiles is that they're integrable. So oftentimes, actually, a lot of people have just proven limit shape results for them. So this sort of theory can help just extend those rather quickly to arbitrary profiles. So, okay, let me just take a few minutes to recall the setup, which is these 5 little bullet points here. So we have the stochastic six-vertex model. Its height function is hn, and it's defined on this upper half plane, z cross z greater than or equal to 0. The initial data is converging to some function psi, for some one Lipschitz function psi. And I'm going to let little psi denote the derivative of psi. So the height function the derivative of the height function is kind of giving you the density of arrows. So the height function is giving you the cumulative sum of the number of arrows, and the derivative is giving you the density of arrows, more or less. So we want to show that n inverse times h of n converges to this entropy solution, to this PDE, with this initial data. And I'll define little h to be minus the x derivative of capital H. So again, this is the density profile for the vertical arrows. So then h is measurable. It's measurable because of Rademacher's theorem. I mean, if you have a one-Lipschitz function, then its derivative exists almost everywhere. And it's the entropy solution to this slightly modified equation. Partial of y of h is equal to partial of x of phi of h. And with this initial profile, h of x of 0 is equal to psi prime x. Okay, so this is the setup, and the limit shape proof is based on an idea of Bahaduran, Gyol, Ravishankar, and Sada, who were trying to who were showing hydrodynamical limit theorems for attractive interacting particle systems. I won't tell you what an attractive interacting particle system is, but yeah, okay. These are models, these are certain models in stochastic dynamics. Anyway, so the proof is based on a certain characterization of the entropy solutions to this PDE by 3 properties. And I'll tell you what these properties are on the next slide. Okay, so the first is a finite speed of discrepancy property, or sometimes called finite speed of propagation. The second is a certain stability, or a stability under perturbations for the height function. And the third is what I had hinted at before, which is that you get the right answer on Riemann profiles, which are sort of double-sided step profiles. Okay, so the first thing is that these 3 properties characterize the solution, uniquely characterize the solution to this entropy, to this PDE. So you can actually just take that. I never told you what an entropy solution to this PDE was, but you can take that as a definition if you like. The second part of this program is to show that these properties hold for the model. They hold with very high probability, approximately, for the stochastic model under consideration. So combining these 2 facts, you'll get the limit shape result you want. Okay, and the advantage to this sort of approach is that it doesn't require substantial use of the Markov generator. There are a huge number of ways to prove limit shape results for interacting particle systems, but a lot of them require you to use the generator. And as I mentioned before, the fact that you have to update these things left to right kind of makes handling that generator a pain. So okay, now I'm going to try to talk to you about what these 3 things mean, and I'll do that. Okay, so this is all in the continuum for the moment, so I'm not going to talk about any stochastic model yet. I'll get there later. So we'll let L0 denote a set of compactly supported measurable functions on R to 0, 1. So these are, you should view these as sort of density profiles. For any t greater than or equal to 0 and any u in this L0, I'll let this p t of u denote h of xt, or h is the entropy solution to the to this density PDE. So del y of h plus del x of phi of h is equal to 0. Oh, sorry, this should be equal. There are a lot of typos here. Sorry, this should be equal and not plus equal to 0. But I think hopefully you know what I mean. With the initial data given by u. So basically all this is saying is that I take the initial data u, I run this thing for time t, and that's my pt of u. Okay, so this is now a semi-group operator in the sense that it satisfies pt plus s is equal to pt of ps. Okay, so now I'm going to introduce a series of properties for another semi-group on L0. And if it satisfies these 3 properties, then it's going to be equal to p of t. Okay. So the first is, as I said before, finite speed of discrepancy. So what that means is the following. So there exists a finite constant nu greater than 0, so that whenever u and v are such that they coincide in some interval a, b, then q of tu and q of tv don't coincide in a, b exactly, but they correspond in sort of a shrink down version of it. So like a plus nu t, b minus nu t. So you can imagine like a fire burning on either end of AB at speed nu, and after time t is the part of the interval that's still left after time t is the part of the interval that they still coincide on after time t. Okay, the second is height stability. So what that basically means is that if u and v are close at time 0, then they stay at least that close for all time. Okay, so this should be u and q sub t. If delta of u, this we'll define in a moment, of qt of u and qt of v, most between the so between u and v. So now this delta of f and g, minimum overall x of h of f of g minus h of f of x minus h of g of x, where this h is simply the integral of f. So remember that I'm dealing here with the I've passed the derivative functions to sort of densities. So what this delta is doing is it's computing the difference back on the level of height functions. So I can view this h of f as sort of the height profile associated with this density profile. So that's height stability. What it means again is that the height profiles are close after a long period of time or after any period of time if the initial data was close. And the third property is that they coincide. So Q and P coincide on Riemann profile. So Riemann profile is just a step profile. So it's rho to the left of 0 and lambda to the right of 0. Okay. So now if you have these three properties, so finite speed of discrepancies, height stability, and Riemann profiles. So the first is that P satisfies them all. This is just the known property of entropy solutions, these what are known as hyperbolic conservation laws or Euler laws, that P satisfies all three of these properties. But the second, the claim is that if Q satisfies all these three properties, then it had better be equal to P. So yeah, that's a characterization of P. Okay, so the statement of this claim, to my knowledge, was essentially in that work I'd mentioned before. But I mean, the idea was more or less, it's more or less 40 years old or 50 years old. I mean, it's due to work of Glim, who was trying to basically simulate solutions to these PDEs. So if you run the simulation and sort of just prove what happens at each step, you kind of get this result. So I guess in the last 10 minutes, what I want to do is twofold. I want to give you an outline of the proof of this claim, and then I want to tell you how these three properties look for the stochastic model. Okay, so let me start with the former. I'm going to outline the proof of the claim, and that is the following. Okay, so what we want to show is that for any, ignore the epsilon. So for any u in this L0, so compactly supported measurable u, and for any s greater than 0, q of s of u is equal to p of s of u. So, okay, so I'm not going to belabor this point, but I can assume that u has finite variation. So its derivative is L1. I can actually assume that u is smooth by height stability and density. So, I mean, you know, smooth functions are dense, and height stability tells me that I'm not afraid of little perturbations. So, with those together, I can assume that u has finite variation. Now, the lemma, which is totally elementary, it's a paragraph to prove it. I won't do it. Is the following. So if u has finite variation, then I can approximate it by a simple function in the following way, with the following property. So what I want is for the simple function, I want the approximation to be strong, but the steps of the simple functions to be relatively large. So in particular, what I'm going to want is for the error to be epsilon. For any epsilon, I want the error to be epsilon times the step size. Okay, so let me describe what I mean here. So there's going to exist x1, x0, x1 all to xm, and rho 1, rho 2 all the way to rho m with the following properties. So first of all, the distances between the x's has at least delta. So what that's telling me is that the step sizes are always at least delta. And the second is that I'm going to define this simple function, u of delta of x, which is, so it's equal to rho of I on this interval xi minus 1 to xi. Okay, so it's a simple function on, it's just a constant, it's piecewise constant on each of those intervals. Then we have that the distance between this delta distance between u delta and u is delta times epsilon. And what's important here is, again, that the ratio, you know, it's not so hard to prove that you can approximate any function by simple functions. But what's important here is that the step size to error ratio, the error to step size ratio is small. It's bounded above by epsilon. So the claim is that for any epsilon greater than 0, I can cook up such a simple function. Okay. So, okay, so now how does the proof of the claim work? I'll try to outline it. The first thing you do is you approximate u up to u error epsilon delta using the simple function u delta, which each has step size delta. Okay, so let me assume for simplicity that each of these x's are just delta spaced. So I'll assume that xk is delta k for each k. So then the restriction of u to any interval of length 2 delta, so k minus 1 delta times to k plus 1 delta, is exactly a Riemann profile, right? It's you know, it goes like this and then it goes like this or something like that. So it's exactly a you know, like this and then it goes like this. If I restrict to an interval of size 2 delta, it's a Riemann profile. Okay, so by finite speed of discrepancies and coincidence on Riemann profiles, what I have is that what you can show is that qt of u delta is equal to pt of u delta whenever t is less than delta over 2 nu. So let me quickly describe how that works. It's not so hard. So by finite speed of discrepancies, what I can do is I can compare qt of u to pt of f on a slightly shrink version of this integral, on this interval. Okay, like if I run time for time delta over 2 nu, then by finite speed of propagation, I've only shrunk the interval on each side by delta over 2. So by shrinking delta over 2 on each side of this interval, I know that qt is equal to qt of u is equal to pt of f on this slightly smaller interval. And likewise, what I know is that pt of u is equal to pt of f, again, because p satisfies finite speed of propagation on this interval here. And then if you take the union overall k's, so I mean, you've taken a bunch of intervals and you shrink them down a little bit, but these intervals all overlap by delta originally. So if I just shrink everything by delta over 2, these intervals are going to exhaust the whole R. So that basically tells you that if you just run time for delta over 2 nu, then the results are the same. Then P and Q match. Okay, so okay, I'm not going to go through all these inequalities here, but what you show, I mean, okay, let me just look at the. Okay, so okay, maybe I can quickly do it. So QT, so if I look at this delta distance, the fact that delta is a metric, the first inequality here is just the triangle inequality. QT of U is close to QT of delta plus QT of delta, PT of U delta, PT of U delta, PT of U. I'm just applying triangle inequality here. Then the middle guy is 0 by what I described before. And these first and third guys by height stability are just bounded by the distance between their initial profiles, U and U delta. So you get the difference between them is 2 times delta of epsilon. So the moral that you can kind of get from this is that, and I'm trying to write out this inequality here, is that if I run for time delta over 2 nu, so the moral is this statement here. If I run time for delta over 2 nu, the error I accumulate is 2 times delta epsilon. So I iterate this thing, say, you know, delta over this many times. So so that's about 1 over delta times. And then I multiply 1 over delta times this error. So that's going to give me a total error of something. So, okay, basically it's 1 over delta times 2 delta epsilon, which is some multiple of epsilon. I mean, you can go through all the constants here and you get that it's less than a constant multiple of epsilon. So now the result, of course, follows from letting epsilon tend to 0. I've shown that QTU and PTU differ by at most epsilon for any epsilon, so that does the job. Okay, so now what I just want to do is tell you what these 3 properties, finite speed of propagation, height stability, and coincidence on Riemann profiles look like in the discrete model. So this is where the work goes, more or less. Okay, so the finite speed of propagation is the following. So if I take 2 stochastic 6-vertex models whose initial data coincides on this interval AB, then they can be coupled. I can couple the dynamics of these 2 models so that they coincide on the slightly shrinked interval A plus nu t, B minus nu t times 0t with high probability, with exponential probability in t. Okay, so the proof of this result is based on a coupling for certain types of colored stochastic 6-vertex models. Okay, the second property is the height stability. So if I consider 2 stochastic 6-vertex models with the height functions h1 and h2, I'll assume that h1 minus h2 initially is at most a. And I also pick some function f. So you should view f as something deterministic. So the way in which this is going to be kind of used is that you pick F to be like the solution to that PDE I was describing before or something like that. So F is deterministic. So the statement is that if H is close to F, by some B, then H1 minus is close to F, then H2 is close to, H2 is also close to F. So okay, if I imagine that H1, F is actually just equal to H1, this is what this is really telling you is that H1 minus H2 at time t is at most A, which is basically exactly the height stability. So the proof of this height stability is based on a coupling, but it's actually a different coupling from this one. So oddly enough, the colored stochastic six-vertex model coupling does not imply height stability. So you have to cook up a different, somewhat implicit and ad hoc coupling to prove this proposition. And the third statement is that the coincidence on the Riemann profiles. So right, so the statement is that for any rho and lambda, the limit shape result holds if I take a double-sided Bernoulli profile. Now, not on the quadrant, but on Z. So to the left of 0, particles come in with property rho, and to the right of 0, arrows come in with property lambda. So if rho is at least lambda, which the experts will know corresponds to a rarefaction fan, this is more or less implied by results of Alexei and myself from 2016. If rho is less than lambda, then there's a shock in the model, and actually the exact solvability doesn't quite work as well. But you can still import probabilistic ideas from Angelveris and Liggett. So actually, a lot of the work comes in the second bullet. In these 3 steps, a lot of the work really comes in this proving the coincidence of the Riemann profile and these shock profiles. Anyway, so I was planning on giving an outline of this first proof of this first proposition, but I guess I'm out of time. So let me just skip it and summarize. So my goal was to analyze asymptotic behaviors of the stochastic six-vertex model with arbitrary initial data and free exit data. So we got a limit shape result and the local statistics result. So the limit shape result showed that the limit shape converged to an entropy solution to a certain PDE. And this is sort of closely related to hydrodynamics for interacting particle systems. The local statistics result showed convergence to a pure state with the correct slope, with the slope S5S, and it's sort of like a convergence to local equilibrium result for interacting particle systems. A result I didn't really belabor on too much was this non-existence result for pure states of the stochastic six-vertex model. And the reason I at least find it interesting is that it's not present for simply attractive models. And the proof of this limit shape is based on a characterization of the continuum solution by 3 properties and showing that they also hold in the discrete. So with that, thanks for your attention and sorry for going slightly over.
Okay, well, thank you very much, Amol. It was an exciting survey of a lot of great work. We have time for questions if anyone wants to unmute themselves and shout something out. So I'm just curious, actually, in the case of proving the shock, so those original works that you were mentioning were for ASAP?
Well, they were for typical attractive interacting particle systems.
I see. Okay,
particle systems that can be coupled with this higher rank, with the sort of colored model. Yeah, those results kind of use the generator of the model, but a lot more lightly, so you can kind of get around it there.
I see.
Yeah.
So to show the shock, you basically couple to 2 different initial datas and then kind of give some sort of sandwiching argument, or how?
No. So for the fan that works, so because that work of Alexei and myself didn't actually apply to all Riemann profiles, it applied to step, and one of the it was step Bernoulli. So on one side the density was 0, but using the thing you described, you can extend it to arbitrary Riemann profile, or arbitrary Riemann profiles with this restriction, lambda is at least rho. For the shock, it's somewhat different. You have to sort of locally look at what the flux looks like around a certain yeah. So you kind of have to. Okay, so what do you have to? Okay, so it's a little bit more complicated. What you have to do is you have to prove a convergence to local equilibrium result there by classifying all kinds of local equilibria, and then you have to analyze what's going on in the local equilibrium. It's a little bit more complicated.
Okay. So it draws on your earlier work. about local equilibrium for stochastic six-vertex?
No. So actually, that for double-sided Bernoulli profiles, that's easier to prove.
Okay.
Yeah.
Any other questions, Evgeny? I thought he took himself off. Okay, well, so if not, let's all thank Amol again, and so we will have another talk in a week. I need to look to see who, but I'll email people, and I'll also email people about the symposium next week, this One World Symposium. That should have a lot of interesting activity, including Li Chang giving another version of his talk. And Martin Heyer also giving some relevant talks and others. Okay, so I'll see you all next week.